Good morning, everyone. Today, in this video, we will start discussing a new topic, which are the halogenated organic compounds. Halogenated organic compounds can be classified into either aliphatic compounds, which are the alkyl or alkyl halides or the haloalkanes, and aromatic compounds, which are the aryl halides. You can have the halogen directly attached to a benzene ring, and these are the aromatic aryl halides, and they will be discussed in full details in another video. However, if the halogen is attached to an aliphatic carbon, which is a carbon not a part of the ring, these are the alkyl or the aliphatic halo compounds. These are the main topic of this video, the alkyl halides or the aliphatic halogenated organic compounds, and we will discuss them in full details. You will have an aliphatic carbon that is attached to a halogen. This carbon is not a part of an aromatic ring. These are the aliphatic halogenated compounds known as the alkyl or alkyl halides. They can be classified into primary, secondary, or tertiary. This is one classification, and the second classification is the geminal or vicinal dihalides. These are two main classifications of these halogenated compounds. If they are monohalogenated, we classify them into primary, secondary, and tertiary. If they are dihalogenated, we classify them into geminal and vicinal dihalides. Let's first discuss the first classification. What is the meaning of primary and secondary and tertiary alkyl halides? Let's first refer to a primary carbon. What is a primary carbon? A primary carbon is a carbon attached to only one carbon. A secondary carbon is a carbon attached to two carbons. A tertiary carbon is a carbon attached to three carbons. This is the definition of a primary, secondary, or tertiary carbon. So now if we are dealing with a primary alkyl halide, it's going to be a compound having a halogen attached to a primary carbon. A secondary alkyl halide, it's a compound having the halogen attached to a secondary carbon. A tertiary alkyl halide is a compound that has a halogen attached to the tertiary carbon. These are the primary and secondary and tertiary alkyl halides. If we refer to the dihalides, the geminal is the compounds where they have two halogens attached to the same carbon. The vicinal dihalides are a compound that has two halogens attached to two adjacent carbons. They have to be adjacent. If they are separated, if they are like that, this is not a vicinal. This is a dihalide, which is not geminal nor vicinal. It's just a regular dihalide. So these are the classification of these compounds. Now, if we move to their nomenclature, nomenclature of these compounds are as we are used to, either common names or EUPAC names. The common names, it considers the halogen as the parent, so it will end in the word halide, and then we will have the name of the alkyl part. So it will be an alkyl halide, exactly the same way as the name of the whole class. So for example, if we have something like that, what is my halogen? It's a chloro, so it's the chloride. This is the parent. And then what is the alkyl part? It's the ethyl. So this is the ethyl chloride. If we go to the EUPAC nomenclature of the same compound, EUPAC nomenclature relies on specific rules stating that you will have to find the longest chain containing the highest priority functional group, and then you give it the name of the alkane that has this number of carbons, and then you remove the suffix of the alkane, the A and E, and you place the suffix of the functional group you are dealing with. and then you start numbering your compound from the side that gives this functional group the least possible numbering. If both sides are the same, then try to give the other substituents the least possible numbering. So in such a case, if we have such a compound, the chain is a 2-carbon chain, so this is the ethane. We leave the ane because this functional group does not have a suffix, and we say that this is the 1-chloroethane. We do not have to mention the 1 because it does not have any other options. It's always a 1-chloroethane. Okay, if we have a longer chain, for example, and then we have the halogen here, so the longest chain here is a 5-carbon chain, so this is the pentane, and it's the 3-chloropentane, and so on. If you have other substituents on the chain, you will have to specify their positions. We have a very important common name for a very important alkyl halide, which is the benzyl halide. Notice that this is an aromatic compound. It's true that it's an aromatic compound because it contains a benzene ring. However, it's an aliphatic alkyl halide. Why is that? Because your halogen is directly attached to a carbon which is not part of the benzene ring. These are what we call the aralkyl classes, where the compound itself is aromatic, however, the functional group is aliphatic. So this is the benzyl chloride. Regarding the geminal dihalides and the vicinal dihalides, when you are nomenclating geminal and vicinal dihalides, in case of the EUPAC nomenclature, again you will number such a compound. So this is a propane, and you have 2 halogens on carbon number 1. So this is the 1,1 di, say chloro, for example, if the halogen is a chloro, propane. However, in case of the vicinal, so these are the geminal, they will be 112233. You will have the same number repeated twice, and then the di, the prefix di, followed by the name of the halogen, and then the name of the chain. In case of vicinal dihalides, you will have 2 successive numbers. For example, 1,2-dichloropropane, 2,3-dichlorobutane, 3,4. It will always be in the form of 2 successive numbers. So this is how we nomenclate these compounds. If we take a look at the organized slides, we will have, as we have said, the primary alkyl halides, the secondary and the tertiary. We said that the primary will be attached, the halogen will be attached to a primary carbon. In case of the secondary, the halogen will be attached to a secondary carbon, and in case of the tertiary, the halogen is attached to a tertiary carbon. Then we discussed their nomenclature. As we said, the common names is just alkyl halide, and we have a very famous one, which is the benzyl halide. And then we have the EUPAC nomenclature, where we name the alkane as the parent, and then we number the compound and state the position and name of the halogen present. As we said, we have a second classification in case if we have dihalo compounds. We have the geminal and the vicinal dihalides, where the geminal will have the 2 halogens on the same carbon, the vicinal will have the 2 halogens on 2 adjacent carbons. And as we said, you just nomenclate them as if they are regular substituents, stating their positions and names. Now we start with the synthesis of these compounds. These compounds can be synthesized through 4 different methods. In all cases, you are actually halogenating a compound. You can either halogenate an alkane, you can halogenate an alkene, You can halogenate an alkyne and you can halogenate an alcohol. As you have already studied, alkanes can be halogenated using free radical substitution reactions. You just substitute one of the hydrogens of the alkane using the halogen in UV and very high temperatures. You substitute one of the hydrogens by halogen. In case of alkenes, you can just add the halogen either in the form of hydrogen halide, giving monohalogenated compounds, or you can add a halogen molecule, giving the dihalogenated compound. In case of alkynes, again, you will add the hydrogen halide, giving the geminal dihalide compound, or you can add a halogen molecule to your compound, giving the tetrahalogenated compound. Finally, the halogenation of alcohols, where you replace the OH of the halogen with a the OH of the alcohol with a halogen. You can do this using one of several methods. You can either use hydrogen halide in presence of zinc chloride, and this will remove the OH and give you the alkyl halide. However, if this alkyl halide, if this alcohol is a new alcohol where your carbon having the OH is attached to a new carbon carrying 3 methyl groups, and you use this reaction, what happens is that the OH leaves, putting a positive charge here, resulting in a methyl shift, and then you end up with a product that is not exactly what you expected, where the halogen moves to the second carbon, not on the carbon of the OH, but to the carbon that is adjacent to the new carbon. This is to produce more stable carbocation, where at first, when you had this carbocation, it was a primary. When you perform the methyl shift, moving the methyl group to this carbon, you will place the positive charge here on a tertiary carbon, producing a tertiary carbocation which is more stable. So this is one method. The second method is if you use the phosphorus trihalides, and the third method is when you use thionyl chloride. The preferable method is the thionyl chloride, because the byproducts of this reaction will be the sulfur dioxide gas and the HCl gas, facilitating the purification of such a product, where all the byproducts are gases, so they will just be removed very easily from the reaction. However, the thionyl chloride method involves highly acidic byproducts, which is the HCl gas produced, which if your starting material is acid sensitive, will be a drawback for this reaction. So if your starting material is acid sensitive, you will have to go to the phosphorus trihalide or the hydrogen halide in presence of zinc chloride if you are not afraid of rearrangement. If you are afraid of a rearrangement, you will have to stick to the phosphorus trihalide. If your starting material is not acid sensitive, you will prefer to go to the thionyl chloride for the ease of the purification of such a product. So as we have mentioned, the synthesis of these compounds involve either free radical substitution of alkanes, or it can involve the addition reactions to alkenes, either by Markovnikov or anti-Markovnikov, resulting in your product, or you can have the vicinal dihalide if you add a halogen molecule. You can add your hydrogen halide either by Markovnikov or anti-Markovnikov to alkynes, so you have alkanes, alkenes, and alkynes. Alkanes by free radical substitution, alkenes and alkynes by addition reactions, either Markovnikov or anti-Markovnikov. And then you can produce them from the alcohol by substitution of an OH by the halogen. As we said, you have 3 main conditions that can be used: hydrogen halide in presence of zinc chloride. However, as I have mentioned, if you use this method, you will remove this OH, placing a positive charge on this carbon. This is a primary carbocation, so a methide shift takes place to place the positive charge on the second carbon, giving a tertiary carbocation, and the halogen ends up binding to the tertiary carbocation rather than the primary. As you see, the primary is the minor, while the tertiary is the major. To prevent such rearrangements, you can use the phosphorus trihalides or the thionyl chloride. As we said, the thionyl chloride is very preferable because the byproducts are the gases, sulfur dioxide, and the hydrochloric acid, which are both gases and can be easily removed, and accordingly the compound can be obtained in pure form. However, if my starting material is acid sensitive, the byproducts, which is the hydrochloric acid, they might decompose or break down my compound, and preventing such a reaction from taking place. Accordingly, I will have to use the phosphorus trihalide. Now, if we move to the reactions of these compounds, they have three main reactions. First, let's discuss the structure of alkyl halides. As you can see, you have a halogen attached to a carbon. Halogens are highly electronegative, so they will attract the electrons of the bond towards themselves, ending up or resulting into a partial negative charge on the halogen and a partial positive charge on the carbon. Accordingly, the main type of reactions that can be used is nucleophilic attack on this carbon. You can actually use a nucleophile that will attack the carbon directly attached to the halogen. The nucleophile, after the attack, will throw away or throw out the halogen from the molecule and take its place. This is a substitution reaction, and this is the main reaction of alkyl halides. The second reaction of alkyl halides can be that if you place a metal, which is magnesium, this is known as Grignard reagent synthesis. When you put a metal in between the carbon and the halogen, when you react an alkyl halide with metal, magnesium metal, the magnesium will be placed in between the carbon and the halogen. Before the metal enters the structure, your carbon is carrying a partial positive and your halogen is carrying a partial negative due to the high electronegativity of the halogen. However, when you attach or you put a metal in between, metals are highly electropositive. Accordingly, the carbon will be more electronegative than the metal, and thus the carbon will carry a partial negative charge and the metal will carry the partial positive charge. So what you actually have done is that you have inverted the charges on the starting material. At the beginning, before the metal, you had the positive on the carbon. By the end of the reaction, you have a negative on the carbon. So you are actually inverting the charges by using the metal. Finally, the third type of reactions are the elimination reactions, when you actually use a base to remove a hydrogen halide molecule and give the alkene compound. So now let's discuss these reactions in full details. First, we will start with discussing the Grignard reaction or the Grignard reagent synthesis. In such reaction, we have an alkyl halide, as we have mentioned. The halogen is carrying the partial negative, the carbon is carrying a partial positive. You reacted with magnesium metal as a first step to introduce the metal in between the carbon and the halogen, and this reaction has to be performed in dry solvents like dry ether to avoid the presence of water, which will end up precipitating your magnesium in the form of magnesium hydroxide. So you have to use dry solvents to avoid the precipitation of your magnesium in the form of magnesium hydroxide. As we said, the product will have a partial negative on the carbon rather than a partial positive, and the partial positive will be carried by the metal. This reaction is performed to convert the alkyl halide into a weak nucleophile. Now the R of the alkyl halide is carrying a partial negative, and accordingly it will start acting as a nucleophile rather than an electrophile, and it can be used to attack any other carbon that is carrying a partial positive charge. So this is the Grignard reaction. As for the substitution reaction, as we have mentioned, in general, the reaction includes the substitution of a halogen by a nucleophile. The nucleophile is carrying a negative charge or a lone pair of electrons or partial negative charge. The carbon is carrying a partial positive charge, so the nucleophile attacks the carbon, removing the halogen and takes its place. This is the general reaction of substitution of alkyl halides. However, this reaction takes place through two different mechanisms. We have the SN1 mechanism and the SN2 mechanism. It can proceed either by SN1 or SN2. We will discuss both mechanisms in full details and the effect of such mechanism on the product obtained. Let's first start with the SN2. We say that this is called the bimolecular nucleophilic substitution reaction. Why is it a bimolecular? It involves the procedure or the mechanism that we have just discussed. You have the carbon attached to the halogen, and then your nucleophile attacks the carbon, removing the halogen. At the beginning, you will have the carbon, which is attached to the halogen, is now attached to a nucleophile. The bond between the halogen and the carbon is weakened, so it's just in the form of dots. And the bond that is now being created between the nucleophile and the carbon is still weak. It has not been formed yet. And the other bonds, the other three bonds, are present on the carbon. This intermediate is very unstable. Accordingly, this is a very slow reaction because it's moving from a stable moiety, which is the alkyl halide, into a very unstable pentavalent carbon. As you see, the carbon is bonded to 5 different moieties. And since carbons are not pentavalent, so this is a very unstable product. It quickly moves in a fast step towards removing the halogen, and the nucleophile is now attached to the carbon. So the first step, which is the rate determining step, we usually say that the slowest step in the reaction is the rate determining step of the reaction. It determines the rate of this reaction since it is a very slow step. It involves two moieties, the nucleophile and the alkyl halide. Both are present in the first step. So this is a bimolecular nucleophilic substitution because the rate determining step is controlled by two molecules, the nucleophile and the alkyl halide. And this is why we say that this is a bimolecular. We denote it, or we abbreviate it as SN2. The two stands for the two molecules. The N stands for nucleophilic and the S stands for the substitution. So this is a bimolecular, two molecules involved in the first step, substitution, nucleophilic substitution reaction. How is this affecting my product? Or why do I care about whether it's moving by this mechanism or the other one? Because it affects the stereochemistry of the product. It does not affect the product itself if it's drawn in a 2D form. However, it will affect it if we discuss its stereochemistry. The stereochemistry of the product is affected. How is that? As we have said, you have the halogen already attached to the carbon, and then you have a nucleophile attacking. To give a simple example of such a procedure is that when we discuss supermarkets. If you have a supermarket and you have people entering the supermarket and people leaving the supermarket at the same time, if they use the same door, this will be a disaster. They will be pushing and pulling each other. They will be in each other's way while some of them are entering the supermarket and some are leaving the supermarket from the same door. This will end up into accidents. Some people will be pushed, some people will fall, some people will be stepped upon, which is not acceptable. So the preferable thing is to have a door for entrance and a door for exit. And these two doors need to be as far away from each other as possible so that people would not be in each other's way. You need to put them away from each other. The people entering the supermarket should be entering from the farthest direction away from the exit door to avoid collision or pushing and accidents between the entering and the exiting people or clients. So this exactly is the same. In case of SN2 reactions, you have the halogen and the nucleophile. One of them is entering and the other is leaving at the same moment. As we have just mentioned, you have the carbon. It will be partially attached to the halogen and partially attached to the nucleophile. One of them is entering and the other one is leaving at the same time. So they cannot do this from the same direction. What happens is that your nucleophile needs to attack from the back side of the halogen. So if your halogen is on the right, your nucleophile needs to attack from the left. If your halogen is on the top, your nucleophile will need to attack from the bottom, and vice versa. It's always attacking from the back side of the halogen. It sees where the halogen is and it attacks from its back side. It goes to the back side of the halogen, of the carbon carrying the halogen. It sees where the bond between the carbon and the halogen is and it goes to the other side. If it's on the right, it will go to the left. If it's on the left, it will go to the right. It will attack from the other side. This will end up into inversion of the configuration. If you already have the halogen attached on the right side, and say for example, and this is the R configuration of your compound. Now when you have the product, your nucleophile will be attached to the left. As you can see, the halogen is here, so you're actually attacking by your nucleophile from that side. So the halogen is on the right and the nucleophile is on the left. So if this is an R, your final product is definitely an S. You have inverted your configuration. So whenever you are performing an SN2 reaction, if you start with an R, you end up with an S. If you start with an S, you end up with an R, because you have inverted your configuration due to the backside attack of the nucleophile. So this is the first effect, the first reaction, the first mechanism of the reaction that can be used for performing a nucleophilic substitution reaction, where both reagent and starting material are present in the first step. When we go to the SN1 mechanism, as you can guess from the name, it's going to be a nucleophilic substitution reaction involving one molecule. This is a unimolecular. You have just replaced the 2 by a 1. So instead of 2 molecules in the starting material, or the 2 molecules in the first step, in the rate determining step, you will have only 1 molecule. What is this molecule? It's going to be the alkyl halide. What happens in the SN1 is that you have the alkyl halide. The halogen leaves by itself before any attack from the nucleophile, leaving a carbocation, which will be attacked by the nucleophile, giving the product. As we have mentioned before, usually the first step that produces charged moieties is the slowest step. As you can see, you have only the alkyl halide present in the first, or the slow, or the rate determining step. The nucleophile does not enter and it's not involved in the reaction except after the intermediate is formed, or the transition state. This is a transition state until the transition state is formed. So it's not really a part of the first slow step. This is why we say that this is a unimolecular reaction. Let's see how such a reaction will affect the stereochemistry of your product. If you actually have the carbon attached to the halogen and it has 3 different bonds, you can draw it in this form as we draw compounds that are that have a stereoisomer. So now when the halogen leaves, the carbon will be an sp2 carbon. An sp2 carbon is a planar carbon. It's in the form of a paper. It's as if you have a surface of the paper. The carbon is drawn together with its 3 other attached groups on one paper, on one plane. It's a planar compound. Accordingly, when you have an attack from the nucleophile can attack from both sides, the same side that the halogen was present in and left, or the other side, because you have a planar compound. If your plan is drawn in the form of a horizontal line, if your molecule is drawn in the form of a horizontal plane, then your nucleophile can attack from the top of this plane or from the bottom of this plane. So if we draw this, if you have your piece of paper like this in a horizontal form, you have your carbon and your 3 other bonds drawn on the paper, your nucleophile can attack from the top or from the bottom. If you draw your piece of paper in a vertical way, your carbon is drawn on a vertical paper, your nucleophile can attack from the left side or from the right side. It's always coming from the other side or from the other 2 planes from on which the carbon atom and attached groups are not present. You have a plane and the attack comes from the other sides of the plane. Okay, so you will have a 50% option that your nucleophile comes from the left hand side and a 50% option that your nucleophile comes from the right hand side. So you end up with 2 products, one of them having the nucleophile at the right hand side and the other having your nucleophile at the left hand side. This is a 50% chance and this is a 50% chance. So you end up with a mixture of a 50% of both enantiomers. So you actually end up with a racemic mixture. What is a mixture having 50% of both enantiomers? It's a racemic mixture. So as we can see, if we perform the SN2 mechanism, we will end up with inversion of configuration. So if we start with an R, we will end up with an S, and if we start with an S, we will end up with an R, while if we perform an SN1 mechanism, we will end up with a racemic mixture. So if we start with an R, we will end up with a 50% R and 50% S, and if we start with an S, we will end up with the same 50% R and 50% S of the compound. Let's see, when do we get this and when do we get that? When do we get the SN1 mechanism and when do we get the SN2 mechanism? And what are the examples of nucleophiles that we have? The nucleophiles that you have are anything, your nucleophile can be anything that carries a negative charge, such as cyanide group, hydroxyl group, alkoxides group, thiol group. All these are acetylenes, for example, groups. All these are compounds that have a full negative charge. It can be something that carries a partial negative charge, like a Grignard, for example, where its R will carry a partial negative charge. It can be anything that carries a lone pair of electrons, like a molecule of water. The oxygen of such a molecule will have a lone pair of electrons. A molecule of alcohol, such a molecule, its oxygen will carry a lone pair of electrons. And amine, where both where the nitrogen will have a lone pair of electrons, ammonia molecule, where its nitrogen will have a lone pair of electrons. These are different examples of nucleophiles. The nucleophiles that carry a full negative charge are classified as strong nucleophiles, while the nucleophiles that carry a partial negative or a lone pair of electrons are classified as weak nucleophiles. And this is very important because it will affect which mechanism will take place. The strong nucleophiles usually proceed through the SN2 mechanism, while the weak nucleophiles usually proceed through the SN1 mechanism, and I will explain in full details why. So let's look at the factors affecting or causing the two mechanisms to take place. Which mechanism will take place? We have two factors since we are dealing with two reactants. We have the alkyl halide and we have the nucleophile. Let's first look at the alkyl halide. In case of the SN2 mechanism, you will have a backside attack. You have a carbon attached to three different groups in addition to the halogen, and you will have a backside attack of the nucleophile. So as the smaller the groups that are attached to the carbon, the easier the reaction, because your nucleophile can penetrate through them and reach the carbon, attacking it to produce the reaction. So you need small groups on the carbon. And the smallest groups that can be dealt with in organic compounds are the hydrogen. Hydrogen is the smallest atom present in organic compounds. So now, if you have these as hydrogens, this will be a very easy reaction. However, if one of them is converted into an R, if one of them is an R, this is a little bit making the reaction difficult, since the nucleophile now has a bigger group that it has to go through it. This is producing some sort of a steric hindrance in the structure, resulting into difficulty of such a reaction. If two groups on the carbon are alkyl groups, this is making the reaction more difficult. If the three groups present on the carbon are alkyl groups and none of them are hydrogens, this is a much difficult reaction, since now the nucleophile has to penetrate through these big groups rather than the small hydrogens. Let's look at what we have just said. If you take a look at this compound, this carbon is attached to three different carbons. So this is actually a tertiary carbon alkyl halide. This is a tertiary alkyl halide. This one is attached to two carbons. So this is a secondary alkyl halide. This one is attached to one carbon. So this is a primary alkyl halide. And this one is not attached to carbons at all. This is the methyl alkyl halide. So if we arrange them according to their ease of performing SN2 reactions, we will notice that the methyl is easier than the primary, easier than the secondary, easier than the tertiary in performing SN2 reactions. Let's look on the other type of reaction, which is the SN1 mechanism. In case of the SN1 mechanism, what happens is that the halogen leaves the molecule, giving a positively charged carbon. As we have mentioned in previous videos, a tertiary carbocation is more stable than a secondary, more stable than a primary, more stable than a methyl. So the formation of this carbocation in case of tertiary alkyl halides is easier. So this is the ease. This is the direction of ease of the SN1. This is the easiest one for performing the SN1 mechanism, and this is the hardest or the toughest one to perform the SN1 mechanism, since the carbocation of such a compound is not stabilized at all. However, the tertiary carbocation is stabilized by the inductive effect of three carbons attached to it. In case of the secondary, you will have only two stabilizing groups. In case of the primary, you will have one stabilizing group by induction. In case of the methyl, you have no stabilizing groups whatsoever, and accordingly, it's the least stable. So if we look at what we have just said, in case of the SN2 mechanism, it prefers the methyl because it does not have any steric hindrance, than the primary, then the secondary, then the tertiary. And if we look at the SN1 mechanism, it will prefer the tertiary, then the secondary, then the primary, then the methyl. So they're exactly the same. When you see a tertiary alkyl halide, you will think directly of the SN1 because it prefers the tertiary. The tertiary prefers the SN1 mechanism, and it definitely does not like the SN2 mechanism due to the steric hindrance. And if you see a methyl or a primary alkyl halide, you will definitely think of the SN2 mechanism because it's preferable for it, and you will exclude the SN1 because it's not preferable for such an alkyl halide. The secondary stands in the middle. You cannot decide whether it's SN2 or SN1 mechanism because it can actually use both. The steric hindrance is not huge since you only have 2 groups that the nucleophile has to push through, not 3 groups. And at the same time, the stabilization of the carbocation is acceptable because you have 2 inductive effects. So you actually have to choose which mechanism. It's either SN2 or SN1, and it can perform both. So which one do you choose? It will depend on the second molecule, which is the nucleophile. As we have said, we have 2 types of nucleophiles. It's either a strong nucleophile or a weak nucleophile. As I've said, the strong nucleophile prefers the SN2 and the weak one prefers the SN1. Now we will discuss why, or the causes for such preference. Why preference? Why does the strong nucleophile prefer the SN2 mechanism, and why does the weak nucleophile prefer the SN1 mechanism? What is the meaning of a strong nucleophile? As we have mentioned, a strong nucleophile is something that is carrying a full negative charge, which means that it's highly unstable. It's carrying the electrons of another molecule, which is a huge load. It's carrying a heavy load that it needs to get rid of it. So whenever it finds anything, even if that thing is just carrying a partial positive and it doesn't really need electrons that much, it will still attack to give it the extra electron that it has. It's carrying an extra electron that it's trying to get rid of. So it will definitely try to push it on anything that it sees on its way that is in even the slightest needs of an electron. So this is why a strong nucleophile prefers or goes through as an SN2 mechanism, where the carbon is just carrying a partial positive. It's not really in huge need of electrons, and still your nucleophile will attack it because it's really trying to get rid of the electron that it's carrying. As in case of a weak nucleophile, the weak nucleophile, as we have mentioned, is something that is carrying a partial negative charge or a lone pair of electrons, which means that it's not really carrying an extra electron. These are the electrons of the atom. It's carrying them. These electrons are the regular load of the atom that the atom is used to. It's not an extra charge. No other atom have just thrown its electrons on this atom. So it's carrying a regular load. So to attack, the molecule that is attacking should carry a full positive charge. It will not give the electrons to an atom that is carrying a partial positive charge. This means that this atom is not really in desperate need for electrons. So the nucleophile will not go ahead and give it its electrons. It's really not that of an emergency. This case is not an emergency for the carbon. It does not need that much electrons, so the nucleophile will not give the electrons. However, when the halogen leaves and the carbon is now carrying a full positive charge, this carbon is desperate for electrons. It's in desperate need. It really needs electrons. So this is when the nucleophile, the weak nucleophile, will really attack. It will sacrifice its regular electrons that it really needs them. The nucleophile really needs its electrons in this case, since it's just a partial negative or a lone pair of electrons, and it will still sacrifice and give the electrons to the carbon because it's carrying a full positive charge. So this is why a nucleophile, if it's strong, it will go through the SN2 mechanism. If it's a weak nucleophile, it will go through the SN1 mechanism. And this is how we choose in case of secondary alkyl halides. The secondary alkyl halide can go through or can employ or can perform both mechanisms, SN1 and SN2. So if I have a secondary alkyl halide and I add a strong nucleophile to it, it will proceed through the SN2. However, if I add a weak nucleophile to it, it will proceed through the SN1 mechanism. So these are the factors that will decide or determine which mechanism will be used, whether the SN1 or the SN2 mechanism. So if we look at the slides, the organized slides for these two reactions up till this point, we have, as we said, the carbon carrying a partial positive. It can react to produce the Grignard reagent, where we reacted with magnesium in presence of dry ether to avoid presence of water, to invert the charges on the carbon attached to the halogen from being a partially positive carbon to a partially negative carbon. And we have the second type of reaction, which is the nucleophilic substitution reactions, where the halogen is substituted by a nucleophile. And as we said, this can proceed through SN1 or SN2 mechanism. The SN2 or the bimolecular, it involves the backside attack of the nucleophile on the alkyl halide. It gives a very unstable transition state, which includes the carbon attached to 5 different groups. The bond between the halogen and the carbon is still partially present, and the bond between the nucleophile and the carbon is still partially being formed. This is the slow step, and then the fast step is when the halogen leaves. As we have said, this is a backside attack, which will have a huge effect if we are dealing with a chiral carbon. The carbon attached to the halogen is a chiral carbon, and the compound is a stereoisomer. If we start with an R compound, we will end up with the S, which means that we have conducted inversion of configuration. In case of the unimolecular substitution reaction, as we have said, the halogen leaves first, putting a full positive charge on the carbon, which will be then attacked by the nucleophile, giving your product. The slow step involves only the alkyl halide. And as we have said, we have attack from both sides. It will attack from the back side and from the front side, giving a 50% of each product, and accordingly, it will give the racemic mixture of the starting compound. So if you are starting with an S, you will end up with 50% S and 50% R. And if you're starting with an R, you will end up with 50% of each again. As we have said, examples of nucleophiles are, as we have mentioned, anything that is carrying a full negative charge, a partial negative charge, or a lone pair of electrons. Regarding the factors affecting such a reaction, as we have said, you can have the structure of the alkyl halide as one factor, and the other factor will be the structure of the nucleophile or the nature of the nucleophile. We have 2 more factors, which are the solvent and the temperature used, but we will not discuss them. It will complicate things more. So let's just stick to the nature of the alkyl halide and the nature of the nucleophile. As we have said, in case of SN2 mechanism, it needs to have as much smaller groups attached to the carbon as possible to avoid steric hindrance, since we have a backside attack. So the methyl will be more preferable than the primary, than the secondary, than the tertiary. While in case of SN1, we are actually producing a carbocation, so we need this carbocation to be stable. So the tertiary will be more stable than the secondary, than the primary, than the methyl, and accordingly this is the order of ease of reaction. As we have said, the nature of the nucleophile, whether strong or weak nucleophile, will affect the type of mechanism employed or done during the reaction. The strong nucleophiles prefer the SN2. This is because they are trying to get rid of the electrons present on them, the extra electrons that were not actually theirs, and they're trying to get rid of them, while the weak nucleophile will never attack before the carbon carries an actual positive charge, so accordingly it will proceed through the SN1 mechanism. This is the order in which the nucleophiles are arranged according to their strength. You have the cyanide as the strongest nucleophile, followed by the iodide, the alkoxide, the hydroxyl, and then finally the things that are carrying a lone pair of electrons as the alcohol and the water of molecule. Now we will move to the exceptions of such rules. We have exceptions to these rules. You can have sometimes a primary alkyl halide and still it can proceed, or it can perform the reaction through an SN1 mechanism. We have three examples, three very famous examples for such an exception. These are the allyl halides. As we have mentioned, the allyl halides are compounds that have 3 carbons. These are mentioned in full details in the alkenes and in the alkynes videos, where the allyl and the vinyl are explained. An allyl halide is a compound that has 3 carbons, 2 of which have a double bond in between, and then the third is carrying the halogen. This is an allyl halide. The allyl halide, as well as the benzyl halide, can perform the SN1 mechanism, even though these are primary. As you can see, the halogen is attached to a carbon which is primary. It is only attached to 1 carbon. As you can see, it's only attached to 1 carbon. So it is a primary alkyl halide. Still, they can proceed through the SN1 mechanism. Why is that? As you remember, we were not able to perform the SN1 mechanism on the primary alkyl halides because once the carbon is carrying a positive charge, stabilization is very weak due to the only one induction of 1 carbon on this carbocation. However, in case of allyl and benzyl halides, when the halogen leaves and the carbon carries a positive charge, this positive charge is stabilized by resonance. Resonance is a very strong means of stabilization, as we have mentioned before. So accordingly, this is a stable carbocation, and accordingly, it can perform an SN1 mechanism. So this is a possible mechanism, an SN1 mechanism. Again, in case of the benzyl, upon losing the halogen, the benzyl will carry a positive charge that will be stabilized by 3 resonating structures, where the positive charge will be moved to the ring and stabilized by the 3 double bonds of the ring. This stabilization will be discussed in full details. How this resonance takes place will be discussed in full details in the aromaticity video. So you have several resonating structures which stabilizes this compound. Accordingly, the benzyl and the allyl can react through SN1 mechanism if they are reacting with a weak nucleophile. They can, at this point, use the SN1 mechanism. The third exception, as we have mentioned, is the neo compounds. The neo compounds are compounds having a carbon carrying 3 methyl groups and another carbon. This carbon, this 4th carbon, will be carrying the halogen. This is a neopentyl compound. In this case, again, the halogen is attached to a primary carbon. As you can see, the carbon attached to the halogen is attached to only 1 carbon. So this is a primary alkyl halide. However, it's not going to react through an SN2 mechanism, because as you can see, it's true that it's attached to only one carbon. However, there is a huge steric hindrance at the backside. Any nucleophile that is attacking will have to go through all this bulky group. So this is one problem. The second thing is that if the halogen leaves, placing a positive charge on this carbon, a very important type of stabilization will take place, which is the methide shift. So now you will have the positive charge placed on a tertiary carbon, and you will have the tertiary carbocation. So this was a primary carbocation. When you had a methide shift moving the positive charge to this carbon, you have just moved it to a tertiary carbocation, which is a stable carbocation. And now the halogen, now the nucleophile will attack this tertiary carbocation, giving the nucleophile on a totally different carbon than the one that we expected. As you can see, when you were performing this reaction, you expected the nucleophile to attack this carbon. It's not true. The nucleophile will attack this carbon because of the methide shift, producing the tertiary carbocation. So, and this reaction can proceed through the SN1 mechanism using a weak nucleophile like water or alcohol. So these are the three major exceptions in which we have a primary alkyl halide and still the mechanism will be an SN1. What are these exceptions? They are the neopentyl compounds or the neo-alkyl halides. They are the allyl halides and the benzyl halides. These three exceptions will react through an SN1 mechanism, even though the alkyl halide is a primary alkyl halide. We have a fourth exception, where the reaction will not proceed at all. If you have a vinyl halide is a compound which has a halogen directly attached to a double bond. You have a double bond and the halogen is directly attached to one of the two carbons of the double bond. This is called vinyl halides. These compounds, if you react them with any nucleophile, whether strong or weak, they will give a negative reaction. Why is that? A double bond is an overlap between two p orbitals, as we have said. Now you have your halogen. Now you have your halogen attached to this double bond. The lone pair of electrons of the halogen are present in an orbital which is parallel to the 2p orbitals. As you can see, this orbital is parallel to these 2p orbitals. So now your overlap will involve the lone pair of electrons of the halogen. Accordingly, we say that this bond is not really a single bond. It's a partial single, partial double. And that's why it's very difficult to break this double bond. And accordingly, this reaction gives a negative reaction. You cannot break the bond between the halogen and the vinyl group. If we take one application of the allyl halides that will show a difference in the product due to the SN1 mechanism, we can use such an example. This is your allyl halide. You will substitute the terminal carbon with an R. Now, if you run this reaction using SN1 mechanism, you will place the positive charge on the primary carbocation of the allyl group. Now you will have resonance to stabilize the product or the transition state that you have, placing the positive charge on this carbon. Now, this is a secondary carbocation, which is more stable. Accordingly, the nucleophile will have to choose between the primary and the secondary. Definitely it will choose the secondary. So the product, your product will be totally different because you have just performed an SN1 mechanism. This is your major product, while your minor product will be the one that you expected, where the nucleophile, this is a minor product, where your nucleophile replaced the halogen. This is where the nucleophile replaced the halogen on the primary carbocation, giving a minor product, while when we do the resonance, we will find that the nucleophile will attack on the other part of the allyl. The allyl has two terminal carbons, the one carrying the halogen and the one carrying the double bond. It will not attack the one carrying the halogen, it will attack the other one because of the stability of the secondary carbocation. And this example really proves the fact that alkyl halides proceed the reaction through an SN1 mechanism rather than an SN2 mechanism. If it proceeded through an SN2 mechanism, this would have been the major product of this reaction. So as we have said, you have three exceptions, which are the allyl, it proceeds through SN1 due to the resonance. You have the benzyl, it proceeds through an SN1 mechanism due to the resonance. You have the vinyl, which will not react, it will give a negative reaction. This reaction will never be performed using nucleophiles. Here it will proceed through the SN1, and here it will proceed through the SN1 mechanism. As we have also mentioned, we have the neopentyl. As we have said, you have a carbon attached to 3 methyl groups and then a 4th carbon which is attached to the halogen. It proceeds through SN1 mechanism because once the halogen leaves, putting a positive charge on the CH2 of the neopentyl group, a methyl shift takes place, placing the positive charge on a tertiary carbon which will be attacked by your nucleophile. Another example of the neo carbons, again you have the neo butane, but you have an additional substitution on the carbon carrying the halogen. Again the halogen leaves, putting a positive charge on the CH of the alkyl halide. A methyl shift will take place. This was a secondary carbocation. Once the methyl shift takes place, it gives a tertiary carbocation, and accordingly the nucleophile will attack this carbon, ending up into a major product having the nucleophile attacking this carbon and the methyl moving here in place of the halogen. A third example, or another example, where we are employing both the vinyl and the allyl concept is this example. You have here 3 carbons, 2 of which are having a double bond in between them and the other 2 are having a single bond. You have a halogen separated from the double bond by 1 carbon, which is the allyl halogen, and you have a halogen directly on the double bond, which is the vinyl halogen. When you react this compound with a nucleophile, the allyl halogen will be replaced by the nucleophile, while the vinyl halogen will give a negative reaction. Finally, the example where the allyl is proven to really proceed through SN1 mechanism, indicating 2 different products. One of them is major, where the resonance took place, placing the positive charge on a secondary carbon rather than the primary carbon, and the nucleophile will attack this secondary carbon.